A few years ago, a planet 124 light-years away briefly became the most likely place for alien life that humanity had ever found. Headlines said we'd detected the fingerprint of living things in its atmosphere, and recently, a team did the obvious next thing. They pointed two of the most powerful radio telescopes on Earth straight at it and listened for 33 days across the entire orbit of the planet for any sign that someone over there was broadcasting. This is what they heard. And honestly, the silence is the less interesting half of the story. The more interesting half is what happened to that original "we found life" claim while nobody was looking. Because it's one of the cleanest examples I know of how easily we talk ourselves into seeing something that isn't there. This is First Signal. Today, let's go through the whole arc of K2-18b, why it electrified astronomy, why that excitement quietly fell apart, what the search for a radio signal actually involved, and why a result of nothing might be more useful than you'd think. To understand why anyone bothered aiming radio dishes at this specific world, you have to know what makes it unusual. K2-18b isn't like anything in our solar system. It's what astronomers call a sub-Neptune, about 2.6 times the radius of Earth and roughly 8.6 times its mass. So it's far heavier than a rocky planet, but much lighter than Neptune. We don't have anything in that size range nearby, which already makes it scientifically valuable. What pushed it from interesting to obsession is where it sits. It orbits a small, cool, quiet red dwarf star right in the middle of the habitable zone, the band around a star where temperatures could allow liquid water. And that fed into a tantalizing idea, that K2-18b might be a hycean world. The name combines hydrogen and ocean. The theory is a planet wrapped in a thick hydrogen atmosphere, sitting on top of a single global ocean, possibly hundreds of kilometers deep. I want to flag something right away because it matters later. Hycean worlds are a hypothesis, not an established fact. Some researchers have argued that planets like this might not be able to exist at all, that under the surface you'd find scorching gas or molten rock instead of a calm sea. So even the ocean world foundation of this story was never settled. Then JWST looked at its atmosphere, and the data got genuinely exciting. The telescope picked up methane and carbon dioxide, and, just as tellingly, almost no ammonia. In planetary science, that particular combination is often read as a hint of an ocean lurking beneath the clouds. So far, so promising. And then came the announcement that put K2-18b on every front page. A team led by Niku Madhusudan at Cambridge reported a possible detection of a molecule called dimethyl sulfide, DMS, in the atmosphere. First in 2023, and then with a stronger claim in 2025. Here's why that word landed like a thunderclap. On Earth, DMS is produced almost entirely by life, mostly by marine plankton in the oceans. It's part of the smell of the sea, so finding it in the air of a distant ocean world wasn't just another chemical detection. It was, potentially, the first time we'd ever smelled biology on another planet. For a few weeks, it really did feel like the line had been crossed. But there's an old rule in science, and it exists precisely for moments like this. Extraordinary claims require extraordinary evidence. And under that standard, the DMS claim slowly came apart. The first problem was the data itself. Independent teams went back through the JWST observations and found the signal was buried in noise, what astronomers call red noise, and wasn't statistically strong enough to stand on. The molecule that supposedly proved life might just have been a pattern in the static. In fact, the same wiggle in the data could be matched by several other molecules entirely. The second problem was deeper and more damaging. A team at the University of Colorado Boulder showed that DMS doesn't actually need life to exist. They reproduced it in the lab through pure photochemistry, sunlight driving reactions in an atmosphere, no organisms involved. And other groups, including a team in Grenoble, found DMS forming in places where biology is flatly impossible, in interstellar gas clouds, in the chemistry around the centre of the galaxy, even in comets. The universe, it turns out, has several recipes for this molecule, and only one of them is alive. By 2025, a paper landed with a title that didn't leave much room for interpretation. K2-18b does not meet the standards of evidence for life. The consensus had shifted. The hycean superplanet teeming with plankton was, for now, hype. A beautiful story that the evidence couldn't carry. And this is where most coverage stopped. The "Life on K2-18b" headlines faded. Everyone moved on, and the planet quietly went back to being one more uncertain dot in a catalogue. But a group of SETI researchers looked at the same situation and asked a different, bolder question. Fine, the chemistry isn't proof of life, but it's still one of the best habitable candidates we have. So instead of sniffing its atmosphere for the byproducts of microbes, why not check for something microbes can't make? Why not listen for a radio signal? This is the part I find genuinely clever, so let me walk you through how you actually hunt for an alien broadcast, because it's not what most people picture. A team led by C.D. Tremblay aimed two of the world's most powerful radio instruments at the K2-18 system, the Very Large Array in New Mexico and the MeerKAT array in South Africa. This wasn't a quick glance. They monitored the system for about 33 days across a wide range of frequencies, from roughly half a gigahertz up to 10, and crucially, across the planet's entire orbit. What they were hunting for is something called a narrowband signal, a transmission squeezed into one very precise frequency, like a single radio station sitting at one exact spot on the dial. That specificity is the whole point. Nature is messy. Pulsars, gas clouds, black holes, they all broadcast across broad, smeared bands of frequency. A razor-thin signal at one pure frequency is extraordinarily hard to produce by accident. It's close to a technological fingerprint. The catch is that we have become incredibly loud. Between cell networks, aircraft, and tens of thousands of satellites like Starlink now overhead, the sky is drowning in our own radio chatter. So the real challenge in modern SETI isn't pointing the dish, it's separating one possible whisper from another planet out of an ocean of our own noise. To do that, every candidate signal had to survive a gauntlet of filters, and the way they're built is genuinely clever. 3 of them are basically automatic cleanup. Anything sitting on a frequency we already know belongs to human technology, gone. Anything too faint to trust, or so strong it was obviously something local, gone. And anything parked at a perfectly fixed frequency, gone too, because Earth spins and the planet moves, so a real signal from K2-18b should slowly drift, and one that never drifts is ours. It's the last 2 filters that are beautiful. They aimed the telescopes at K2-18b and at other nearby stars at the same time. A true signal from the planet should appear only in the beam pointed straight at it. If the same blip lit up every beam at once, it was just interference washing over the dish from the side, discarded. And then they used the orbit itself. When the planet swings behind its star, anything broadcasting from it should briefly vanish. So a genuine candidate had to disappear at exactly the right moment and come back on the other side. After all of that, after processing millions of candidate hits through every one of those filters, here's where it landed. Nothing. Every single candidate failed. Each of the millions of blips turned out to be terrestrial interference or an artifact in the instruments. Not one of them was a clean, narrowband, drifting, planet-locked signal. The sky around K2-18b, at least in the frequencies we can hear, was silent. But a careful null result is not the same as learning nothing. Because they listened so hard and heard so little, the team could set a hard ceiling on what's there. If anyone is living on K2-18b, they are not pointing anything at us more powerful than the giant Arecibo radar that we ourselves used to operate before it collapsed. There could still be a civilization there, it just isn't shouting in our direction with a beam we'd recognise. Now, it would be easy to file this under disappointing and move on. I'd argue that's the wrong raid, for 2 reasons. The first is practical. This search was a proving ground for the techniques we'll need on the next generation of telescopes, instruments like the Square Kilometre Array, which will be able to scan thousands of worlds with this exact filtering approach. They didn't just check one planet, they sharpened the tool we'll use on the rest of the sky. The second reason is stranger, and to me, more profound. A researcher named Daniel Angerhausen has argued that every empty search quietly tightens the math on how alone we are. The logic goes like this. If we carefully survey, say, 40 to 80 promising worlds and come up empty on all of them, that itself implies that fewer than perhaps 10 to 20% of such planets carry detectable life. Each silence narrows the odds. We learn the shape of the answer not by finding something, but by carefully cataloguing where it isn't. And there's a quieter thread running under all of this that I can't stop thinking about. We listen for radio because we invented radio. In the 1960s, just as we started filling our own skies with broadcasts, we assumed any other civilization would be doing the same, and we aimed our antennas outward, expecting to overhear them. It's worth noticing how much of our search for the alien is shaped by whatever we happen to be doing at the time. A century earlier, when humans were digging canals across continents, astronomers convinced themselves they saw canals carved across the surface of Mars, and an entire dying Martian civilization to go with them. There were no canals. There was the spirit of the age, projected onto a bloody red dot. That pattern should make us humble. The DMS story was the modern version of it. We wanted the ocean world so badly that, for a moment, the noise looked like life. Catching ourselves doing that in real time and walking it back is not a failure of science. It's the entire point of science working correctly. So where does that leave K2-18b? Still one of the most interesting worlds we've ever found, just no longer the one we were ready to crown. The possible ocean is still possible. The atmosphere is still worth studying. JWST will keep watching it, and the bigger telescopes coming online will listen far deeper than 33 days ever could. We aimed humanity's best ears at the most promising planet we knew of, and the universe gave us silence. But it was a useful silence, the kind that makes the next search a little sharper, and the kind that, every time it happens, tells us a little more about how rare the thing we're standing on might actually be. The search for a voice out there has always quietly been a search for context on ourselves, and we just learned a little more about how unusual it is to be the ones doing the listening. We'll come back to this the moment the next telescope hears something, or, just as importantly, the moment it doesn't. Until then, keep looking up. This is First Signal.